So hello everyone, this is lecture 13 for the nuclear physics. In the last lecture we have stated that what are nuclear reactions and what are the Q values, and we have seen the Q values for alpha decay, beta plus decay, beta minus decay, and now we need to discuss some questions based on the nuclear reactions. So today we will discuss them. So let's see. First question is, an alpha particle is emitted from the decay of americium Am at rest. That is, this is the reaction. Now rest masses of americium, uranium and alpha are given. That is just 224.54 giga electron volt divided by c square. This is the mass units. 220.811 giga electron volt divided by c square for uranium. For alpha it is 3.728 giga electron volt divided by c square respectively. Now they ask us that what is the kinetic energy of alpha particle in mega electron volt. So we know for the alpha particle in terms of Q value, the formula A by A minus 4, kinetic energy of alpha particle equal to Q. This formula we already know. So first we need to find for this Q value. So Q value we just simply subtract this mass from this mass, that is mass of americium minus mass of uranium minus mass of alpha, multiplied by c square. Now this is in giga electron volt, so c square will cancel out and you will get giga electron volt. Now we need this in mega electron volt, that's why we'll convert this into the mega electron volt, multiply 10 to the power 3, give you 5 mega electron volt. Just equate this with this. You know already A and A minus 4, that is for the americium 241A, and 241 minus 4 will give you that. And now you can just find the K alpha. And if they ask you to find the kinetic energy of this uranium also, so you can simply find, means see initially it was in rest, so if you find the Q value by kinetic energy, that will be kinetic energy of product minus kinetic energy of reactant. This is 0, so it is simply kinetic energy of this plus this. So the kinetic energy of uranium will be Q value minus kinetic energy of alpha. So this will be your answer if they ask you for the uranium. Next question is Q value of the alpha decay of thorium 232 to the ground state of radium 228 is 4082 electron volt. The maximum possible kinetic energy of alpha particle is closest to. So this is the same question like this. So this is the reaction thorium to radium and alpha particle is decayed. So they ask you that what is the possible kinetic energy of alpha, so K alpha. So you will just simply, you have A, that is 232, A minus 4 will be 228, and this is your formula, use this. And first, and it is Q value is already given, so just equate it here and find the alpha particle kinetic energy. Next question is, if a star can convert all the helium nuclei completely into the oxygen nuclei, the energy released per helium nuclei will be, so helium nuclei is converting into the oxygen, so this is converting into this. So if we write the equilibrium equation, then it will be 4 helium nuclei or atoms will convert into this oxygen. Now we need to find mass of helium is given, mass of oxygen is given, so let's find the Q value. That will be 4 multiplied by mass of helium minus mass of oxygen, multiplied by 31.5. If this mass is given in AMU, then just multiply with this, you will get the energy in mega electron volt. So now you have this energy, and this is for the 4 helium atoms, and they asked us that what is the energy released per helium nuclei, so it will just divide by 4, so that will be your answer. Next is, a star initially had 10 to the 40 deuterons. It produces energy. So deuterons are simply hydrogen atoms which have two mass number, means 1 proton 1 neutron. So that is the reactions, these are given. That's how they produce energy, means this deuteron converting into 3H1P, and this 3H1 again reacting with 2H1 giving 4HED 2 plus neutron. If the average power radiated by the star is 10 to the 16 watt, so by this reaction the average power radiated is 10 to the 16 watt. So deuteron supply of the star is exhausted in a time of the order of, so this is the number of deuterons are available, so how much time it will take to exhaust complete this supply. Now this is given in watt, means this energy joule per second is emitting. So if we say in t time, this will all exhaust, so 10 to the 16 multiplied by t seconds will be equal to the energy of we will find the energy for 1 deuteron and multiply with this, so that total energy will be equal to 10 to the 16 joule multiply t, that energy. So that's how we'll do. So let's first find what is the energy released by 1 deuteron in this particular reaction. So we'll just add these two equations, so that will, this 3H1 will cancel out and you will get 3 multiplied 2H1 equal to 4He2P plus N, and these masses are given for all the deuteron, proton and neutron. So you will get this reaction as I told you. Now you will find the Q value, that will be 3 multiplied mass of deuteron minus mass of helium and mass of proton, mass of neutron, multiply 931.5 because these are in AMU. So this will be your energy. Okay, now this energy is for 3 neutrons, so per neutron it will be divided by 3, and and how many neutrons are available, that is 10 to the 40. So this will be the total energy emitted, and let's say in T time this all 10 to 40 neutrons exhausted. So in T time this is the energy per second is released, so in T time this will be equal to this. So from here you just substitute this Q value from here and find the T, that will be 1.29 multiplied by 10 to 12 seconds. Next is, it is proposed to use nuclear fusion reaction. So this is 2H1 converting to 4He2. A nuclear reactor of 200 megawatt rating. So this is the nuclear reactor, and this is producing this megajoule, you will say, per second. If the energy from above reaction is used with 25% efficiency, so whatever energy is released, only 25% of that energy is used in reactor. How many grams of deuteron fuel needed per day? So this is the amount releasing per second. So we'll just multiply this with 1 day, and you will get the energy emitted in 1 day, and that must be equal to we will find that how much energy is released by 1 neutron, then we will multiply this with that m mass which is required for this, and that must be equal to that. So that's how we'll proceed. So this is masses are given for deuteron and the helium. So power is 200 megawatt, that is 206 joule per second, and in 1 day just multiply with the 24 hours, 60 minutes and 60 seconds. So that's how we'll convert it, that how much energy is radiated in 1 day. And we need to find the mass of deuteron. So how many grams of deuterium is required? So we need to find the mass of deuterium. So first we need to find the Q value. So that is the energy released by the 2 deuteron atom deuterium. So per deuterium will be divided by 2. So that will be energy by 1 deuterium. So let's say m mass is required for 1 day. So m divided by the total atomic mass number, that is 2. That will give a number of moles, and with m mass, so multiply this Avogadro number, you will get a number of nuclei. Okay, and now per nuclei energy is this. So for this number, just multiply this with this, and now this will be energy radiated, and only 25% is used. So that's why 25 by 100 of this energy must be equal to, this is per second, so multiply with 24 hour, and now it will convert into the minutes and convert into the second. So this energy must be equal to this. So you can find m from here, that will be 120.26 gram. And on the basis of the same concept, you have this question. In a nuclear reaction, uranium-235 undergoes fission, liberating 200 mega electron volt of energy. The reactor has 10% efficiency and produces 1000 megawatt power. If the reactor is to function for 10 years, find the total mass of uranium required. So it is working for 10 years. This time is given. So if the reactor has 10% efficiency and produces 1000 megawatt power. So this amount of power it produces. So this multiplied by 10 to the 6 means 10 to the 9 joule per second is energy produced. So 10 years, just multiply this in converting this in seconds. So you will get how much energy is produced in 10 years. That energy must be equal to, if m mass is there for uranium, divided by a, that is the atomic mass of uranium. This will convert into the moles. This is Avogadro number. Now you have the total number of nuclei, and per nuclei it is 200 mega electron volt. So for this number of nuclei, this will be 200 multiplied by this, converted into a joule. So this energy radiated, and now the efficiency is only 10%. So for this energy, only the 10% amount is released. So 10 by 100, this must be equal to that amount, or that energy in 10 years. Okay, so 10 years is converted into the seconds, and this is the 10 to the 9. This is the energy produced per second. So this must be equal to this, and you can find the m, that will be 3.84 multiplied by 10 to the 7. This is a simple concept. You just need to follow the question and you will get your answer. Q value of the following reaction, that is minus 1.3452. This energy Q value is given for this reaction. We need to find the mass of 5B10 in AMU. If the mass of 1s2 2He4 is on the scale of 6E12, so what is the meaning of this scale? That means mass of 6E12 will be simply 12.00 AMU. So this mass is given, these three masses are given, so just find the difference of masses, and that must be equal to Q value, that is this, and you can find the mass of this. How? See, ms2 mc12 minus mb10 minus mhe4. So just take it as x, and this is given, this is given, this is given, and Q value is also given. Multiply this, and you will get your answer for mb10, that is 10.1013 AMU. Next question is, when a 10 mega electron volt 1s2 nucleus bombards a 3 lithium 7 target nuclei, it produces a 4b8 and neutron in nuclear reaction. So this reaction is occur when the this is kinetic energy of hydrogen or the deuterium is given, that is 110 mega electron volt. What we need to find? If the neutrons are observed to emerge at right angle, these neutrons, means there is something collision like, means this is lithium nuclei is simply there and the hydrogen atoms are coming like this, and after that neutrons are going 90 degree, and this barium will go something like this at theta angle. So if the neutrons are observed to emerge at a right angle to the direction of the incident beam, calculate the energy of neutrons and the energy angle of recoil of the acid with 4 Be8 nuclei. So we need to find that angle for the Be and energy also. Okay, means kinetic energy of beryllium. Now masses are given for lithium, for neutron, for hydrogen, and for beryllium. So this is, so see here what is happening. This is your hydrogen or deuterium, and it is striking on the lithium nuclei, and after that this reaction occur. Neutrons are going 90 degree with this axis, and this is your Be, and this is going at theta angle, and kinetic energy of this deuterium is given, that is 10 mega electron volt, and we need to find this theta angle kinetic energy of this Be. Okay, so how you can find? First let's find the Q value. So that will be, and this is in the rest. Okay, so M Li plus mh minus mbe and m minus mn, and these all are given in the AMU. That's why we will multiply with 931.5. So that's how you can find the Q value. And now Q value must be equal to sum of kinetic energy. So this is kinetic energy of neutron plus kinetic energy of Be, and minus this is the kinetic energy of deuterium, because this is at rest. So this is given, that is 10, and we already find the Q value. So 10 plus 14.78, that will give you sum of Be and neutron kinetic energy, that will be 24.78 mega electron volt. Now sum is given, so how you can find the separate? So this is your equation 1. So we need to find the second equation, and we will equate just the linear momentum, that is in the x-axis, that will be under root 2, means this will be under 2 mk. So for this is on the x-axis, this will be momentum of this on the that, so it will be under root mbe kbe cos theta equal to this x-axis only has this momentum, so that will be under root mh and kh, and similarly this sin theta component must be equal to the momentum of this neutron, that will be under root mn kn, that will be equal to mbe kbe sin theta. Now you have these two equations, so you just take the square and sum them, so you will get this equation. And now you have this. From here you need to find the k of Be, so that means you can just write this kbe in terms of the, means kn in terms of the kb, kn equal to 24.78 minus kb, and substitute in place of kn that this minus this, and you will get this equation only in terms of the kb, mean only variable remain will be kb, all other values you will have. So you can find the kb, that will give you this answer. And now you can, if you have one value, now you can find the other one also for the kinetic energy of neutron also, that will be this. And now if you need to find this theta angle, so you just divide this equation by this equation, you will get tan theta equal to this mn by mh, kn by kh, you have kn, you have kh, mn mh, so you can just find the theta, that will be came around 44 degree. So that's all for today. In the next lecture we will start the liquid drop model, and thank you everyone.